Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1874 publication by Georg Cantor, titled On a Question about the Elementary Theory of Aggregates, represents a document of immense conceptual density, its few pages containing the seeds of a mathematical revolution. This essay undertakes a rigorous evaluation of the paper's internal claims, proceeding sequentially through its compact yet profound argumentation. The analysis will focus with surgical precision on the mechanisms, logical structures, and methodical innovations presented within the text itself. The objective is to dissect the work as a self-contained intellectual artifact, examining the validity and ingenuity of its propositions from the definition of its initial subject to its world-altering conclusion. We will explore how Cantor, with a masterful and almost understated rhetorical strategy, constructs a logical edifice that would ultimately provide the very foundations for set theory and a new understanding of the infinite. This inquiry will delve into the specific techniques of enumeration and construction he pioneers, assessing their coherence and the philosophical commitments they implicitly carry, thereby illuminating the work's singular contribution to the landscape of pure mathematics. Section 1. The formalization of algebraic numbers and the assertion of their countability. The paper commences with a claim of deceptive simplicity regarding the set of all real algebraic numbers. Cantor first establishes his object of study with meticulous care. He defines a real algebraic number as any real root of a polynomial equation of the form c sub 0 times x to the power of n, plus c sub 1 times x to the power of n minus 1, continuing through to the final term c sub n equals 0, where all coefficients c sub I are integers. This definition is classical, yet its mobilization within Cantor's framework is entirely novel. The central claim of this initial section is that the aggregate of all such numbers, which he denotes omega, can be put into a one-to-one correspondence with a set of positive integers. This is the property, or Eigenschaft, referenced in the paper's title. To substantiate this claim, Cantor introduces a brilliant organizational principle, a method for ordering the polynomial equations themselves. He defines a quantity he calls the height, n, for each polynomial equation. This height is calculated as the sum of the degree of the polynomial, n, and the absolute values of all its coefficients. For an equation with coefficients c sub 0 through c sub n, the height n is n plus the absolute value of c sub 0 plus the absolute value of c sub 1, and so on, up to the absolute value of c sub n. This construction is a piece of profound intellectual engineering. It transforms an abstract algebraic object, the polynomial, into a concrete positive integer. The claim's validity rests on the fact that for any given integer value of the height n, there exists only a finite number of polynomial equations that can produce it. For example, for a height of n equals 1, the only possibility is the degree n equals 1 and the coefficients being 0, which is trivial. For n equals 2, one could have a degree of 1 and a coefficient sum of 1, such as x equals 0 or negative x equals 0. For n equals 3, the possibilities expand, but they remain finite. One could have degree 2 with coefficient sum 1, or degree 1 with coefficient sum. The evaluation of this claim hinges on the soundness of this mapping. The mechanism is impeccable. By iterating through the positive integers for the height n, starting from 2, then 3, then 4, and so forth, Cantor creates an exhaustive and unambiguous ordering of all possible polynomial equations with integer coefficients. For each height n, he can then find the real roots of the finite set of corresponding equations and list them in their natural order of magnitude. By stringing together these finite lists of roots for each successive height, he constructs an infinite sequence, omega sub 1, omega sub 2, omega sub 3, and so on, that by its very construction must contain every single real algebraic number. The argument is watertight. It establishes a procedure, an algorithm for enumerating the totality of algebraic numbers. The claim of countability is therefore demonstrated constructively. This section showcases a new mode of mathematical reasoning where the possibility of enumeration, even if practically infinite, is sufficient to establish a fundamental property of an entire class of numbers. The method's quiet elegance belies its power, providing the essential, stable foundation upon which the paper's more dramatic conclusion was in Section 2, the constructive proof of a number external to any given sequence. Having established the countability of the real algebraic numbers, the paper's second major argumentative movement presents a theorem of far greater scope and implication. The claim is this: given any infinite sequence of distinct real numbers denoted as omega sub 1, omega sub 2, omega sub 3, and continuing indefinitely, it is always possible to determine a real number, eta, that is absent from this sequence. The proof offered for this claim is a masterpiece of constructive logic, a procedure that builds the desired number step by step. Cantor asks the reader to consider an arbitrary sequence of real numbers. His method then proceeds to define a pair of new numbers, which we may call a prime and b prime, that lie between the first two elements of the sequence, omega sub 1 and omega sub 2, assuming they are ordered by magnitude. This creates the first interval from a prime to b prime. The core of the mechanism is an iterative process of creating nested intervals. Cantor then seeks the first member of the original omega sequence, say omega sub m, that falls strictly inside this newly established interval from a prime to b prime. Having found it, he defines a second, smaller interval bounded by a double prime and b double prime, which is contained within the first interval but specifically excludes the point omega sub m. He continues this procedure indefinitely. At the nth step, he identifies the first number in the omega sequence that lies within the most recently defined interval from a superscript nu minus 1 to b superscript nu minus 1. He then defines a new, strictly smaller interval from a superscript nu to b superscript nu that is contained within the previous one yet excludes this newly identified sequence member. The evaluation of this procedure reveals its logical inevitability. The sequence of left-in points, a prime, a double prime, and so on, is monotonically increasing and bounded above. Symmetrically, the sequence of right-in points, b prime, b double prime, and so on, is monotonically decreasing and bounded below by the fundamental axiom of completeness for the real numbers, which Cantor implicitly assumes as a shared ground of understanding with his audience. Both of these sequences must converge to a limit, because the length of the intervals, b superscript nu minus a superscript nu, can be made to approach 0. These two sequences converge to the same single point. The number he calls the final step of the argument is to demonstrate that this limit point, eta, cannot be any member of the original omega sequence. This follows directly from the construction. For any integer m, the number omega sub m is, at some specific stage of the process, explicitly used to define a subsequent interval from which it is excluded. Therefore, eta, being the limit point contained within all subsequent intervals, cannot be equal to omega sub m for any m. The construction guarantees eta's otherness. The argument's validity is absolute, conditional only upon the acceptance of the completeness of the real number line. This section of the paper is a demonstration of pure intellectual force, a method for generating a mathematical object whose existence proves a universal property about infinite sequences. It is a toolmaker's argument, providing a technique that can be applied to any countable set of reals to produce a number outside of it. The subtle beauty is the proof does little more than follow a set of clear, procedural instructions. Yet the result is an object with world-changing properties. Section 3, the corollary on the uncountability of the continuum. The third and final intellectual maneuver in Cantor's 1874 paper is presented with an air of straightforward deduction, almost as a simple corollary to the preceding theorem. Having proved in Section 1 that the aggregate of all real algebraic numbers is countable, And having demonstrated in Section 2 that for any countable sequence of real numbers there exists a real number outside that sequence, the conclusion becomes inescapable. The claim is that the aggregate of all real numbers, the continuum, is uncountable. Cantor makes this point by wedding the results of his 2 prior sections. He invites the reader to consider the sequence of all algebraic numbers, omega sub 1, omega sub 2, and so forth, which Section 1 proved to be possible to construct. Then, applying the constructive method from Section 2 to this specific sequence allows for the determination of a real number, eta, which is by construction absent from the sequence of all algebraic This number eta, by its very nature of being a real number that is absent from the complete set of algebraic numbers, must be a transcendental number. The paper thus provides the first ever explicit proof of the existence of transcendental numbers, a feat that had eluded mathematicians for centuries. Joseph Liouville had earlier constructed specific examples of such numbers, but Cantor's argument proves their existence as a necessary consequence of the structure of the number system itself. The claim is a profound one. The set of transcendental numbers is abundant. It is the algebraic numbers that are the exception. Evaluating this concluding claim requires assessing its logical dependence on the previous steps. The argument is a syllogism of perfect clarity. Premise 1. The set of real algebraic numbers can be arranged into an infinite sequence. Premise 2. For any such infinite sequence, a real number can be constructed that is provably external to it. Conclusion. There exist real numbers which are transcendental. This logical chain is unbreakable. The further conclusion, that the set of all real numbers is itself uncountable, follows with equal force. If the set of all real numbers were countable, it could be arranged in a sequence, but the theorem from Section 2 shows that for any such sequence, a real number exists outside of it, a direct contradiction. Therefore, the initial assumption of countability for the real numbers must be false. The genius of this section resides in its economy. Cantor uses his own freshly forged tools to resolve a major open problem and, in the same breath, to establish a property of the continuum that fundamentally alters the mathematical conception of number. He reveals a structural asymmetry between 2 types of infinite sets. The claim's power is derived from its constructive nature. It does not merely assert uncountability. It provides a recipe, rooted in the preceding sections, for understanding why it must be so. The paper culminates here, transforming a question about aggregates into a definitive statement about the very fabric of the real number line. The conclusion is so potent because it flows as a direct and irrefutable consequence of the methodical, almost pedestrian, steps that came before. Section 4. The rhetorical, framing and latent hierarchies. A complete evaluation of the 1874 paper requires an analysis of its rhetorical structure and the implicit claims embedded within its presentation. The title itself, On a Question about the Elementary Theory of Aggregates, is a model of scholarly understatement. The question it ostensibly addresses is the countability of the algebraic numbers. This is the explicit focus of the first half of the paper, and the accomplishment that lends the work its name, the truly groundbreaking result. The uncountability of the continuum and the proof of the existence of transcendental numbers is framed as a secondary observation, a corollary derived from the main theorem. This framing is a critical component of the paper's internal strategy. One interpretation of this rhetorical choice is as a measure of prudence in a potentially hostile intellectual climate, particularly given the known skepticism of influential figures like Leopold Kronecker towards concepts of the actual infinite. By foregrounding the more concrete, procedural result concerning algebraic numbers, Cantor presents his work within a more traditional and acceptable mathematical paradigm. The enumeration of algebraic roots via the height function is an argument Kronecker himself might have found more palatable, as it involves finite steps and combinatorial reasoning. The more radical conclusion is thereby softened, presented as a logical consequence rather than a revolutionary declaration. This allows the ideas to enter the mathematical discourse with a minimum of initial friction, a Trojan horse of transfinite concepts hidden within a classical framework. A deeper evaluation suggests that this structure reveals something fundamental about Cantor's own developing thought. The paper is a record of discovery. It builds its case methodically, reflecting a process of reasoning that begins with a manageable infinite set and then uses the properties discovered there to probe a more complex one. The internal logic suggests a hierarchy. The paper effectively establishes two distinct kinds of infinity, without yet naming them. Aleph null and alephone. The set of algebraic numbers possesses an infinity that can be tamed, ordered, and sequenced. The set of real numbers possesses an infinity of a higher order, one that resists any attempt at sequential arrangement. The paper's very structure, moving from the countable to the uncountable, mirrors this nascent hierarchy. The claim latent in this structure is that infinities themselves have a structure and can be compared. The constructor proof in Section 2 is the tool that facilitates this comparison. It functions as a litmus test for countability. When applied to the algebraic numbers, it produces a transcendental number. When applied to the totality of real numbers, it produces a logical contradiction. The paper, therefore, is not merely delivering two separate results. It is demonstrating a powerful new comparative methodology for the study of infinite aggregates. The understated title and the corollary format serve to package this radical new methodology within a form that emphasizes logical continuity over conceptual rupture. It is an argument designed for maximum logical force and minimum rhetorical alarm, a masterpiece of scientific persuasion. Conclusion. In its final analysis, Georg Cantor's 1874 paper stands as a monument of deductive elegance and conceptual daring. The evaluation of its internal claims reveals a logical structure of extraordinary soundness, a chain of reasoning where each link is forged with meticulous precision and depends wholly on the one before it. The initial claim regarding the countability of algebraic numbers is substantiated by the ingenious invention of the height function, a mechanism that flawlessly translates the abstract domain of polynomials into an ordered sequence. This becomes the bedrock for the paper's central constructive argument, a nested interval proof, which demonstrates with irrefutable logic the existence of a number external to any given sequence. This proof, relying only on the accepted principle of the completeness of the reals, is the engine that drives the work to its stunning conclusion. The final claims, the existence of transcendental numbers and the uncountability of the real continuum, emerge not as bold conjectures but as inevitable consequences of the machinery so carefully assembled in the preceding sections. The paper's understated rhetorical posture, framing its most revolutionary insight as a mere corollary, further speaks to a sophisticated understanding of how radical ideas gain purchase in a conservative discipline beyond proving its specific propositions. The work provides a powerful, generalizable method for interrogating the nature of infinite sets, thereby laying the complete and sturdy foundation for transfinite arithmetic. Cantor's essay is a testament to the power of pure reason, a compact demonstration that a few pages of carefully structured argument can permanently alter our understanding of the deepest structures of mathematics.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.